So let's take a closer look at this separating colors using a diffraction grading problem. Okay? It says a mixture of violet light of 410 nanometers in a vacuum and red light 660 nanometers in a vacuum falls on a grating that contains 1 times 10 to the 4 lines per centimeter. All right? For each wavelength, find the angle that locates the first maxima. Okay, and so remember, we're using a diffraction grating here, and we're trying to find maxima, and that relationship is given by this relationship. Okay, so we have two situations here. We have this violet light, and we have this red light. Okay, so we want to solve for theta, right? The angle that locates the first order maxima for each of these. So this will be sine theta equals m lambda over d, and this will be another sine theta equals m lambda over d. All right. Now, if it's the first order maxima, remember, that is just 1, m equals 1. And that's true for both of these. Right? Now, what changes here is the wavelength. So if we're going to substitute this in, the wavelength here says 410 nanometers for the violet. So that's going to be 410 times 10 to the minus 9 meters. And we need to know what this distance is, right? Remember, the distance is the distance between the slits and the grating. Okay? Now, the problem says that we have 1 times 10 to the 4 lines per centimeter. Okay? So how do we turn that into a distance between slits? Well, we just take the inverse of it. We want to find out how many centimeters there are per line. Okay? So if we just do 1 over 1 times 10 to the 4 lines per centimeter. Limes. I'm funny. Then we get an answer of 10 to the minus 6 meters per line, right? So each line is separated by about a micron. Okay, so that's small, right? So you notice that I did a quick conversion there from centimeters to meters. That's because, you know, we want to keep things consistent in meters. It's the SI unit. So we put 10 to the minus 6 meters per line here. If I go ahead and do my inverse sine of all this, I get an answer for violet of 24.2 degrees. Okay. Now, let's do the same thing for red. In this situation, we have sine of theta equals m is 1. Now, the wavelength is going to change. The red light wavelength is 660 times 10 to the minus 9 over the same exact distance between slits, which is 10 to the minus 6. So I just take 10 to the minus 6 meters per line over here. And then I go ahead and do my inverse sine and get a theta of 41.2 degrees. And here we have it. Proof positive. 41.2 degrees versus 24.2. So if here is the diffraction grating, and here's the wall, right? The red light will bend at an angle of 41, right? And this violet light over here, so this is red, and this violet light will only bend here at an angle of 24.2. So that's going to be violet. So this is proof positive that the red light is going to bend more than the violet light, all right? And we see that there's this dispersion effect that happens when we put multiple colors or even white light through the double slits of a grating. All right? It's kind of cool, kind of cool. You can see it with the numbers now, with the mathematics, you know, huh? All right. So let's do a more conceptual question. This next conceptual question says to look at this figure over here. And basically what we have, I almost lost my whole glass right there. Whew, that would have been That would have been bad. I might have lost myself in the process. Okay, so let's suppose that we have a grating, right? And we have two maxima. We have one maxima here, and we see another maxima here. Okay, and then we have, of course, the central maxima here. The question says, one of these is red and one of these is blue light. Which principal maximum is associated with the blue light, the one farthest or the one closest? We basically just proved that. You know this by now. You know how things bend when they diffract or go through a double slit experiment. The longer wavelength is going to diffract more, and so you're going to have more bending in the case of the red light. So this one would be red, and this one would have to be blue. Okay. Second, it says, if the number of slits per centimeter in the grating were increased, right, the number of slits per centimeter were increased, would these two principal maximas move away from the central maximum or move towards the central maximum or remain in the same place? Well, let's just go back to our handy dandy equation. D sine theta equals m lambda, right? Or sine theta equals m lambda over d. Okay, so if I'm increasing the number of slits per centimeter, if the slits per centimeter go up, right, then that means the distance between slits, in other words, the number of centimeters per slit, right, like how far each centimeter is away from each other, is going to go down, right? This is just d, right? The number of centimeters between each slit is d. So that means that if slits per centimeter goes up, then d goes down. D is in the denominator. If d goes down, sine theta goes up, which means that theta goes up. All right, which is kind of cool. So in other words, if the number of slits per centimeter were increased, then the two maximas would move away from the central maxima, like that. Okay? So we're just exploring this simple mathematical relationship that keeps coming up again and again, and using that to make predictions about what might happen if we change certain parameters, like the number of slits per centimeter, the density of the slits in the grating, right? And again, this has real-life consequences for if you're talking about, you know, instead of shining light through some artificial set of slits, you're shining light through a crystal or DNA, for example. All right? So we're going to explore a question about X-ray diffraction in the next video. I'll see you there.